For the next few sections, we're going to continue our study of functions by focusing specifically on what we call polynomial functions. So we've actually seen a few polynomial functions already: the identity parent function, which is f of x equals x, as well as all the other linear functions that come from that are considered to be polynomial. Also polynomial are f of x equals x squared, which is the quadratic parent function, and f of x equals x cubed, which is the cube parent function. So without explicitly defining what we mean by a polynomial, just keep in mind anytime you have a variable raised to an exponent, and that's primarily what's going on, typically what you have is going to be considered polynomial. So in this video, we're going to focus specifically on quadratic polynomial functions, which are just one step up from our linear functions. So what's special about a linear function is the variable has an exponent of 1. So in a quadratic function, the variable typically has an exponent of 2. So anytime we have a function where the variable has a highest exponent of 2, we consider that function to be quadratic. So let's define quadratic functions specifically. So all quadratic functions come from the parent function f of x equals x squared, which was one of the parent functions we saw when we started graphing functions. The graph of any quadratic function is called a parabola. So if you remember, that graph looks kind of like a U shape. If we're graphing f of x equals x squared, then it's essentially a U-shaped graph that's centered at the origin with two tails pointing upward. Every parabola has a couple of key features. The maximum or minimum point on the graph is called the vertex of the parabola. And then the graph is symmetric on either side of the axis of symmetry. So the axis of symmetry is just going to be an imaginary vertical line that goes through the vertex right down the middle of the graph, and it's significant because on either side of this imaginary line we have mirror images. So the axis of symmetry is important because it helps us generate points on the graph. If we're trying to graph a parabola and we can get a point on one side of the axis of symmetry, then we know we also have to have another matching point on the other side of the axis of symmetry. Our primary goal in this section is to be able to generate all the components we need from the function in order to create an accurate graph of a quadratic function. So some of the functions we're going to see are going to be able to be generated from function transformations, from graph transformations, like those we learned in the previous chapter. However, we're also going to see some quadratic functions that we can't graph from function transformations. So once we get to those, we're going to have to deal with their graphs in a little bit of a different way. So we're going to look at two different general forms for how we can write a quadratic function. One, again, that we can graph from transformations, and then one that can't be necessarily graphed from transformations. So our first form for a quadratic function is called vertex form. So vertex form is of the form f of x is equal to a times x minus h squared plus k. So notice if we were to strip anything with addition, subtraction, or multiplication away, we would just have x squared. We would just have the quadratic parent function. So the a, the h, and the k are considered transformations. We're going to talk specifically about what they do to the graph, but we know in general the a out front is going to give us a vertical stretch or shrink. The h inside parentheses is going to be a horizontal shift, and the k outside of parentheses is going to be a vertical shift. So technically speaking, we already have all the information we would need to graph something in this form, but we just want to go a little deeper. We want to use an equation in this form in order to give more information about the function and about the graph as a whole. So we call this particular form vertex form because we can determine the vertex of the parabola just looking at the numbers that we'll have in the function. So the vertex is always going to be h, comma, k. So h is going to be the number that's added or subtracted from x, and k is going to be the number that's added or subtracted after the parent function x squared is applied. So one thing you need to pay attention to here is notice that in the general form, h is subtracted. So remember, x always does the opposite. Whenever there's subtraction, we consider the number that we move to be positive. Whenever the number's added, we move in the negative direction. So it's the same kind of idea here. In order to get the x coordinate for the vertex, which is going to be a point in the coordinate plane, we'd use the opposite sign. So if h is subtracted, we're considering h to be a positive number. If h is added, we're considering h to be a negative number. Now, the opposite is true for k. Anything we do after the function, we just do what the operation tells us to do. So if we're adding k, k is considered to be positive. If we're subtracting k, k is considered to be negative. Once we have the vertex, we can immediately generate the axis of symmetry. So remember, the axis of symmetry is just going to be a vertical line going through the vertex. So every single vertical line is of the form x equals a number. So in this case, it's going to be x equals k. It's going to be the only vertical line that's going to pass directly through the vertex. So it's always x equals whatever the x coordinate of the vertex is. Now, one distinction we need to make is that the vertex is a point and the axis of symmetry is an equation of a line. The reason we want to make this distinction is because when you write the axis of symmetry, the x equals part is very important. The axis of symmetry is a line. In order to give a line, we have to have an equal sign somewhere. We're writing an actual equation that represents this line. So if you just write h and say h is the axis of symmetry, well, h is a number. H is not a line. H is not an equation. It's always something of the x equals form. So it's got to be x equals a number. Then and only then is it something that can represent the axis of symmetry. So once we have the vertex and the axis of symmetry, the other thing we have to decide is how is the graph going to be oriented. So it's possible that we could have a parabola in standard form, just flipped up like normal, that looks kind of like the x squared graph. And it's also possible that we could have a parabola flipped upside down. So in this case, the tails would be pointing towards negative infinity. We decide which way we're oriented based on whether A is positive or negative. So A is the number out front. Remember, having a positive or a negative out front determines whether or not we have a vertical reflection. So if we have a negative sign out front of our problem, that's considered to generate a vertical reflection if we were to treat that as a graph transformation. So if A is positive, both the tails on the parabola are going to be pointing upward. And if A is negative, both of the tails on the parabola are going to be pointed downward. Let's see if we can get a better picture of what we're talking about. So the first possibility is that A is greater than 0. So the leading coefficient outside of the parentheses out front is a positive number. So if A is greater than 0, that means our graph opens upward. So if we were to graph this, we're oriented with the tails of the graph pointing upward. Remember, the vertex is oriented at h, k for the x and y coordinates respectively. And we have that imaginary line that goes through the middle of the graph called the axis of symmetry. And the equation of the axis of symmetry is going to be x equals h, where h is whatever the x coordinate of the vertex is. So notice that on either side of this imaginary vertical line, we have mirror images for our graph. So if we were just going to graph the parent function, f of x equals x squared, notice that the axis of symmetry would actually be the y-axis. The y-axis is that vertical line that goes through the middle of the graph and divides it in half. Once we move our graph around, our axis of symmetry moves as well, and it just so happens that it ends up at the x coordinate for the vertex. It's the line x equals h for whatever h is. So whenever our graph is oriented like this, the vertex is considered to be a minimum with the value of k. So it's a minimum because it's the lowest point on the graph. Any value lower than that we can't actually reach. So the minimum value of the quadratic function is going to be k, which is the y-coordinate of the vertex. So the lowest value we can reach for our function is whatever k is. That's going to be our minimum value for our function. The domain for our function is going to be all real numbers. So remember, from a graph, we can generate the domain by projecting the graph onto the x-axis. So if we were to slide all the points on the graph onto the x-axis, we'd cover the entire x-axis. So our domain is going to be all real numbers. Our range is going to be k to infinity, where k is the y-coordinate for the vertex. So k is going to be the lowest point we can reach in terms of an output for our function. So any value higher than k we can get, any value less than k we can't get. Now, one thing I don't want you to be confused about is here h would be a positive number and k would be a negative number. That's completely arbitrary. So h can be positive, h can be negative, k can be positive, k can be negative. This is just a general example. So h and k can move all around on the coordinate plane, and everything we've just said still applies. It doesn't matter what the exact values of h and k are. These are just general ideas that apply based on the orientation of this graph. The other possibility for our function is that a is less than 0, so our leading coefficient is negative. In this case, our graph opens downward, so that means when we graph the parabola, the tails are going to actually be pointing downward towards negative infinity. However, everything else is pretty much the same. So we still have h and k for our coordinates for our vertex, so h is our x-coordinate, k is our y-coordinate. And we still have the axis of symmetry that goes through the parabola, dividing it in half, and it's always of the form x equals h, where h is the x-coordinate of the vertex. However, in this case, the vertex is a maximum with value k. So in this case, the vertex represents the highest point on the graph. Any point higher than that is not on the graph. Anything lower than that we can reach. So the highest value this function can attain is going to be k. So k is the biggest output we could get for any particular input we'd plug into our function. The domain here is also going to be all real numbers. So you can actually take it to the bank that any quadratic function in any form, any shape whatsoever, is always going to have a domain of all real numbers. We can plug in any number we want and get an output. Here the range is going to be negative infinity to k. So notice if we project this graph onto the y-axis, we have all the values less than k covered, but any value above k is not going to be included in the range. So our range is negative infinity to k. So let's take both of these pieces of information, both of these cases, and let's see if we can actually graph some quadratic functions after generating all the important pieces that we need in order to get a graph. So let's try our first example. So we want to sketch the graph of the function f of x is equal to negative 2 times x minus 1 squared quantity plus 8. So first let's identify our a, our h, and our k. Our a is going to be the number multiplied out front, the h is going to be the number added or subtracted in parentheses, and then the k is going to be the number added or subtracted at the end. So a is negative 2. H is 1. Notice that even though we subtracted, h is going to be a positive number because our general form is x minus a number, so it's going to be a positive 1. And then k is going to be 8. So most of the information we need for our graph comes from just these three numbers. So first thing we want to decide is whether the graph opens upward or downward. So we base this on the value of a. A is negative 2, which is less than 0. Well, if our leading coefficient is less than 0, then that means we're going to open downward. So we know when we graph this particular parabola, our tails should be pointing downward towards negative infinity. Okay, so that gives us a sense of what general situation we're in, how our graph should look in the end. Now let's get more specific. So we want to identify the vertex. The vertex is always going to be the point h, comma, k, whatever those two numbers are. So for our particular parabola, the vertex is going to be the point 1, 8. So this is the first thing you can put on your graph. You can put the point 1, 8 on your graph. So let's keep going. So same function, we've got all our components. Now we want to find the axis of symmetry. So that's the vertical line that goes through the vertex. It's always going to be of the form x equals h. So in this case, the line is x equals 1. So if you're going to put this on your graph, make sure you graph it as a dotted line. It's an imaginary line. It's not actually part of the graph. It's a guideline for helping you graph it. So that's our axis of symmetry, x equals 1. Okay, next we want our intercepts. So the x and y intercepts are considered to be key components of any graph. Regardless of what kind of function we have, we always want to find our intercepts when we're graphing. So if you remember, what's special about an x-intercept is that the y-coordinate is always 0. So in order to solve for x, in order to solve for our x-intercepts, we let y be 0, or in other words, we let f of x be 0, and then we solve for the variable that's left over, which in this case is x. So we're solving for x. We need to get x by itself. So first thing we need to do is move that 8 over. So I need to subtract 8 from both sides. I've got a negative 2 out front, so I need to divide the negative 2 as well. So I'm left with x minus 1 squared is equal to 4. Okay, now in order to do anything with the x, I have to get rid of that exponent. It's squared, so in order to get rid of a square, I need to take a square root. The one thing you have to remember, though, is when you take a square root in an equation, you have to put a plus or minus on one side of the equation in order to indicate that we have both a positive and a negative number that we could square in order to get a 4 in this case. So when we take the square root, the square goes away. We take the square root of the 4, we get 2, and we put a plus or minus on that side of the equation. Finally, one more step, we need to move the 1 over. So we're going to add 1 to both sides. So x is going to be 1 plus or minus 2. So this is actually just a nice compact way of writing two separate numbers. The numbers are 1 plus 2 and 1 minus 2. So our actual x-intercepts are going to be negative 1, which we get from the 1 minus 2, and 3, which we get from the 1 plus 2. So in coordinate form, that's going to be negative 1, 0, and 3, 0. So there's 2 more points you can add to your graph. So we've got our x-intercepts, now let's get our y-intercept. Remember, there's only going to be 1. If we have 1, there's only going to be 1. So in order to get the y-intercept, we let x be 0, and then we solve for whatever the output is when we let x be 0. So we're just plugging in a 0 in place of x. Now it's just an order of operations problem. So I need to simplify inside parentheses. 0 minus 1 becomes negative 1. Now I look for an exponent. So the next thing I need to do is simplify that negative 1 squared. Now an easy mistake to make is you distribute that negative 2, multiply the negative 2 by the negative 1 before you apply the exponent. You can't do that. That's going to change your answer. So make sure you're following order of operations. So we square that negative 1 and we get a positive 1. Now let's see if we can simplify the rest of it in one step. Negative 2 times 1 is negative 2, and negative 2 plus 8 is going to be 6. So our y-intercept is 6. Or in coordinate form, it's going to be 0, 6. So that's the final point you're going to add to your graph. At this point, you can really generate your graph. Remember, it's going to be a U flipped upside down, passing through all 4 of the points we found. So we found the vertex, we found 2 x-intercepts, and we found a y-intercept. So if you graph it correctly, it should pass through all of those pretty nicely, and you should have a nice U-shaped graph. So let's use the graph to find a little bit more information. So first thing we want to do is find the maximum or the minimum value. Which one is it? We need to decide. Well, since we're oriented downward, our tails are pointing downward, we're going to have a maximum. We're going to have a highest point. The vertex represents the highest point we can reach on the graph. And then the actual function value at the maximum is going to be 8. It's the y-coordinate of the vertex. So our maximum value in this case is going to be the number 8. Now let's find the domain and range. So domain, always all real numbers, always. 100% of the time, the domain for this kind of function is going to be all real numbers. Now remember, our range is a little bit different. The range is determined by how we're oriented. So because our graph is oriented downward and our tails are pointing downward, our range is going down to negative infinity, and then it's peaking at the vertex. So our vertex y-coordinate is going to be 8. So 8 is going to be the highest function output we can get. So our range is going to be negative infinity to 8 in this case. So let's summarize all the key information. We found the vertex, we found the x-intercepts, we had 2 of them in this case, and we found the y-intercept. So if you put it all on the graph, you should have something that looks roughly like that. Now keep in mind, this is not an art class. Your parabola doesn't necessarily have to be pretty and perfect. However, you should have all of those key points accurately graphed, and you should be able to generate at least a reasonably accurate graph from those points. Let's try another one. So now we want to sketch the graph of f of x equals 1/2 times x plus 2 squared. So in this case, our a is 1/2. Our h is negative 2, so notice that even though we're adding inside parentheses, it's a negative 2. The general form has x minus a number, so if we're adding a number, we're going to treat that as subtraction of a negative, so h is going to be negative 2. Now there's no number added or subtracted at the end in the place that we normally see a k, which means that k has to be 0. There's an understood 0 tacked onto the end. So the y-coordinate of our vertex is going to be 0. So let's find all the other components we found for the previous graph just with this new function. So is the graph going to open upward or downward? Well, we base that on the value for a. So a is 1/2, which is greater than 0. If a is greater than 0, that means our graph is going to open upward. So our tails are going to be pointing upward once we generate our parabola. What about our vertex? Vertex is always h comma k. So in this case, that's going to be the point -2, 0. Let's keep going. So let's find our axis of symmetry. Once we've got the vertex, that's pretty easy to find. It's always the line of the form x equals h. So it's the vertical line that goes through the vertex. In this case, our h is -2. So our axis of symmetry is going to be x equals -2. So you can put your vertex, you can put your axis of symmetry on your graph, and you're off to a good start. Now what about our x-intercepts? So remember, for an x-intercept, y is 0. So we're letting f of x be 0, and then we're solving for x. So we sub in our rule for f of x. We've got to get rid of that 1/2 out front. So divide both sides by 1/2. Turns out we have a 0 on the right-hand side, so when we divide it out, nothing really happens. We're just left with 0 on the right-hand side still. Now we need to get rid of the exponent, so we need to take the square root. Again, when we take a square root in an equation, we have to put a plus or minus on the other side of the equation apart from the one we're taking the square root of, where we're trying to get rid of the exponent. So we would technically need to put a plus or minus on the right-hand side with the 0, but you may be aware that doesn't really matter. Plus 0 and minus 0 is still the same thing, so it doesn't actually change anything by putting the plus or minus there. So when we take the square root, we're just left with x plus 2 is equal to 0. Move our 2 over, and we have x equals -2. So if we add on the y-coordinate, that's going to be the point -2, 0. So go and see if you can add that one to your graph. If you do, you may notice something weird. You may notice that this is actually the vertex. We've already graphed this point. We're in a special situation where we only have one x-intercept. And if we only have one x-intercept, it just so happens that that's always going to be the same as the vertex. So finding the x-intercepts didn't actually give us any more information than we already had. So let's see what else happens. We're going to have to deal with this at some point, but as of right now, we're just going to keep going. So we found the x-intercept. There was only one of them. Now let's find the y-intercept. Remember, there's only going to be one of these. There will be exactly one y-intercept. So now we're going to let x be 0, and we're going to solve for the output from the function whenever we let the input be 0. So f of 0 means plug in a 0 in place of x. Follow order of operations, so 0 plus 2 is going to be 2. Now make sure you apply the exponent before you multiply. So we have 1/2 times 4. We simplify that down, and that's going to be a 2. So our y-intercept in xy coordinate form is going to be 0, 2. So that's a new point. That one you can add to your graph. So we've got our y-intercept. Now we want to find the maximum or the minimum value of our graph. Well, our graph is oriented upward. Our tails are pointing upward, which in this case means we have a minimum value. We have a lowest point on our graph, and then anything below that, we don't actually have any graph. So in this case, we have a minimum. The minimum value is going to be the y-coordinate of our vertex, which in this case is going to be 0. So that means 0 is going to be the lowest function value that we can get as an output for our function. We can get anything above that. We can't get anything below that. So what about our domain and range? Domain is always all real numbers for a quadratic function. We can plug in any number we want to our function, add 2, square it, and multiply by 1/2. There's no way we could divide by 0. There's no way we could take a square root of a negative number just based on the structure of this function. So our domain is all real numbers. The range is based on how the graph is oriented. So since the graph is oriented upward, we have a lowest point on our range, and then we have all the values above that. So in this case, our range is going to be 0 to infinity. So let's summarize what we found. We found the vertex, -2, 0. We tried to find the x-intercept. Well, actually, we did find it, but it turns out it was the same as the vertex. It didn't give us any extra information. And then we found the y-intercept, which is 0, 2. So if you put all that on your coordinate plane, you'll notice you only have 2 points. Well, 2 points is enough to graph a line, but it's not enough to graph something like a parabola, something that's more complicated. So ideally, we need to find at least one more point in order to get an accurate graph. So since the vertex and the x-intercept are the same, we need to find this additional point. Here's where the axis of symmetry comes into play. So remember, the axis of symmetry is just that imaginary line that goes through the middle of the graph such that we have mirror images on either side of that vertical line. So this is why it helps us. Notice we have 0, 2. We're going to use the y-intercept. 0, 2 is 2 units to the right of the axis of symmetry. So what's significant about the axis of symmetry is that if we have a point that's 2 units to the right, we have to have a matching point that's also 2 units to the left. So we have to have a mirror image point for this y-intercept that's on the other side of the axis of symmetry. So if we go 2 units to the left, we end up at the point -4, 2. The axis of symmetry tells us that for any point on either side, we have to have a matching point on the other side. So without having to do any more algebra, we can actually generate the third point that we need in order to create our graph. So once you add that point to your graph, we have 3 points. We have essentially enough to get a pretty good graph. And our graph should look roughly something like this. So notice the vertex is on the x-axis, so our vertex and our x-intercept are going to be the same. So we've seen a couple of functions in vertex form, which is sort of our preferred form for a quadratic function because we can relate it directly back to graph transformations. However, we have a second form for quadratics that's probably the more common form. It's more likely what you'll see if you're doing an application type problem. So standard form looks like this. It looks like f of x is equal to ax squared plus bx plus c. So notice in this case, everything is distributed out. There's no parentheses, nothing's factored. This is not something that we can graph as a parent function. So the reason we run into a problem is we don't have one instance of an x. We actually have 2 x's here. So if we were to take vertex form and distribute everything out, in other words, square that binomial, that x minus h, distribute the a, add the k. If we were to simplify that all down, we would end up with something in this particular form right here. So because we have an x squared and we have an x, it's not as simple as just saying, okay, this is directly related to the parent function f of x equals x squared. Let me graph it using transformations. Unfortunately, that doesn't work anymore. Now what we do know is this is still going to ultimately look the same when we graph it. It's still quadratic. It's still going to have a graph that looks like a parabola, but the technique we need to use to graph is going to be a little bit more involved. So we still need to find the vertex. We still need to find the axis of symmetry. It's just going to be a little more complicated than it was before. So our vertex, we actually have a formula based on those coefficients, a, b, and c. Those are going to be your actual constants in your problem. We have a formula based on a, b, and c in order to find the vertex. The vertex is always going to be of this form. So the x-coordinate is going to be -b divided by 2a. So you take whatever the second coefficient is, whatever the first coefficient is, and you combine them, -b over 2a. That's going to give you an actual number. That number is going to be your x-coordinate for your vertex. In order to find the y-coordinate for the vertex, you just take that x-coordinate and you plug it into your function. So remember, the whole thing that's valuable about function notation is in order to find an output from an input, we just plug the input we want in, use the rule to simplify everything down, and that gives us the output that matches our particular input. So once you figure out whatever -b over 2a is, plug it back into your function, simplify everything down, and that's going to be your output. That's going to be the y-coordinate for your vertex. Now finding the axis of symmetry really doesn't change. We take that one extra step to find the vertex, and then whatever that number is, it's going to be x equals that particular number for the axis of symmetry. Now one thing that's good news is the a in this form, in standard form, functions the same way as the a in vertex form did. So if you remember, the a in vertex form was responsible for telling us whether or not our graph opens upward or if it opens downward. Well, it turns out this a works the same way as well. This a is what we call the leading coefficient. It's the coefficient for the term with the highest exponent. So it actually works the same way. If that a is positive, our graph opens upward. If the a is negative, our graph opens downward. Everything else works the same way. So depending on our orientation, we have a minimum or we have a maximum. And depending on our orientation, our domain is always all real numbers, but our range may change forms. The only thing that changes in this situation is how we find our vertex, how we find our axis of symmetry, and then what our function looks like. What's going to be a little more involved is finding our x-intercepts. That's typically the hardest part of any problem, is finding the x-intercepts. So we're going to have to do just a little bit more work to find our x-intercepts, but we'll get to that. It's not going to be a big deal. So let's try graphing a quadratic in standard form. So our function is f of x is equal to negative x squared minus 6x minus 10. So again, we're standard form, we're not vertex form. So although we can identify what a is, we cannot immediately identify what h and k are just by looking at the function. We're going to have to do a little bit more work to find those. What we can identify is what a, b, and c are. Remember, we're going to need those different numbers to figure out the vertex. So a, b, and c are the coefficients for each of the terms. So a is -1, b is -6, and then c is just the constant on the end, which in this case is -10. So we can determine the orientation the same way we did before. We base it on the value for a. So a is -1, which is less than 0. If our leading coefficient is negative, that means we open downward. So our tails are pointed downward. Now let's find our vertex. So we have a formula for the vertex, -b over 2a. In this case, b is -6 and a is -1. So we just plug those in. Notice in the numerator we have a negative, negative. Negative times a negative is going to be a positive. Make sure you're really careful with your signs whenever you're using a formula like this, so that negative times a negative becomes a positive. Our denominator becomes a -2. So we have positive 6 over -2, which simplifies to -3. So -3 is going to be the x-coordinate of our vertex. In order to find the y-coordinate of our vertex, we take that number we just found and we plug it into our function. Function notation allows us to take an input and easily find the matching output. So we just plug that -3 in and see what we find. That's going to be our output. Now again, this is an order of operations situation, so make sure you're following order of operations very carefully. There's an exponent here, and then there's a negative out front. Make sure you apply that exponent before you distribute that negative to the -3. So we have to square that -3 before we can do something with the negative out front. So we square the -3, that becomes a 9. We have the negative out front. I went ahead and multiplied the two values in the next term. So we had a -6 and a -3. I multiplied those two together and that became a positive 18. So we have -9 plus 18 minus 10. We simplify that all down and that's going to be -1. So that means our vertex is going to be -3, -1. You can add that to your graph. Okay, now what about our axis of symmetry? Once we found the vertex, we found the axis of symmetry. It's always x equals the x-coordinate of the vertex. So that one's pretty quick to find. Okay, here's where it gets interesting. So now we want to find our x-intercepts. Procedurally, nothing changes in terms of the concept. It's the same idea. So y has to be 0 in order to have an x-intercept. So we say f of x is equal to 0. We set it equal to 0. Well, that means we take the rule for f of x and also set that equal to 0. So now we have a quadratic equation that we want to solve. So this is something you've probably seen in previous math classes. If you're a little rusty on these, this is a good time to go brush up on them. Solving a quadratic equation takes one of two techniques. One, you could potentially factor it. So you want to rewrite the left-hand side of the equation as a product of two factors. Then you can split them up and set them each equal to 0 and you're good. So if it's been a little while since you've done that, we have some review videos posted online. Go watch those videos. Make sure you review factoring if you haven't seen it in a while. Now it turns out this particular equation cannot be factored. There's no way we can factor the left-hand side of the equation. So our option, if we can't factor, is to use the quadratic formula. If you haven't already memorized it, you need to memorize the quadratic formula. Commit it to memory, never forget it. So here's our quadratic formula. The quadratic formula is just a formula we can use involving the coefficients for our quadratic equation in order to put them all together and generate what the values of x would be to make it a true equation. So remember, our a is -1, our b is -6, and our c is -10. These are the numbers that are being plugged into the quadratic equation. When we plug them in and simplify everything down, that's going to give us values for x that represent our x-intercepts. So the algebra looks terrible. I'll admit it. The algebra looks completely terrible. It's really a matter of how detail-oriented and how organized you are. It's really just a lot of bookkeeping. You have to make sure you're really careful when you simplify everything. So if it takes you a few steps to simplify all of that, that's fine. Go step by step. Make sure you don't brush anything under the rug. Make sure you're very careful with your order of operations. So take whatever steps you need. You should be able to get down to this point. So we end up with 6 plus or minus the square root of -4. So everything under the square root simplifies to a -4. All of that divided by -2. So we have a problem here. We've got a square root, and it's the square root of a negative number. That is not a real number. Square root of -4 is not something we're equipped to deal with yet. If that number, whatever that is, doesn't exist anywhere on the coordinate plane, that's not a real number. So if we run into something like this with the quadratic formula, where we have what we'll end up calling an imaginary number, anytime we take the square root of a negative, we have an imaginary number. If we run into something like this that's not a real number, that means we have no x-intercepts on our graph. And unfortunately, there's no way of knowing that just looking at the problem. We have to go through all of this in order to figure that out. But once we get to that point, if we have a negative under the square root, that means our graph does not have any x-intercepts. So practically speaking, that means the graph is either entirely above or entirely below the x-axis. And which one we have is going to depend on how our graph is oriented. So we'll get to that. But in general, just to sum up, there are no x-intercepts. The quadratic formula tells us this. Now we can find a y-intercept. There's always a y-intercept. So let x be 0, plug in 0 in place of x. These are usually really quick to simplify when you're in standard form. So notice the first and second terms completely cancel out. They're just 0. So we're just left with -10. So our y-intercept is 0, -10. Now what about our maximum or minimum value? What do we have here? Well, a is -1. We're oriented downward. So that means we have a maximum. We have a highest value. And it's always going to be the y-coordinate of the vertex, which in this case is -1. So our maximum value is going to be -1. What about domain and range? Well, that doesn't change from vertex form to standard form. Domain is still all real numbers. And because we're oriented the way we are, the range is going to be -infinity to -1. We're oriented downward. We have a maximum. The maximum is -1. So we can have any y value, any function output below -1, just nothing above of it. So let's summarize what we've got. We've got our vertex, -3, -1. We found that from the coefficients a, b, and c. We determined that we don't have any x-intercepts. However, we do have a y-intercept. We found the y-intercept. So we're in a similar situation as the one before. We have 2 points that we can graph, but we need 3 in order to graph accurately. So let's use the axis of symmetry again, just like we did before. We're going to use it with the y-intercept. So the y-intercept, which is 0, -10, if you graph this along with the axis of symmetry, you'll notice that this point is 3 units to the right of the axis of symmetry. Well, the axis of symmetry tells us that if we have a point that's 3 units to the right, we've got to have a mirror image point that's going to be 3 units to the left. So the point that's going to be 3 units to the left of the axis of symmetry is going to be the point -6, -10. So that's our third point. Once we have the vertex, the y-intercept, and then in this case just another point that we found, we can generate our graph, and our graph should look something like that. So let's try one more. So this will be the last one we graph before we move on to an application type problem. So our function is f of x is equal to 2x squared minus 10x minus 5. So standard form again, we don't have h and k, but we do have a, b, and c, which we're going to use to generate all the information we need. So our a is 2, our b is negative 10, and our c is negative 5. Okay, so we're basing it off of all this information. A tells us our orientation. In this case, a is 2, which is greater than 0, which means we're going to be oriented upward. Now what about our vertex? Vertex is always h comma k. In this case, h is going to be whatever negative b over 2a is. So negative b is going to be negative 10. 2 times a is going to be 2 times 2. So this is 10 over 4, simplified down to 5 over 2. Okay, so we have fractions. It's inevitable. We need to be able to deal with them, so we're going to deal with them now. If you can do this example, you can do pretty much any problem you need to be able to do. So the x-coordinate of our vertex is 5 over 2. So to find the y-coordinate, remember we take the x-coordinate and plug it into our function, find the output that goes with that specific input. So we're looking for f of 5 over 2. So wherever we see an x, we're plugging in 5 over 2. Now we're going to have to be really careful with order of operations here because we're applying all these operations to fractions. So we do our exponent first. Squaring a fraction means square the numerator and square the denominator. So 5 over 2 squared is going to be 25 over 4. So this simplifies down to 2 times 25 over 4. I went ahead and multiplied the next two values in the next term. So 10 times 5 over 2. The 10 and the 5 multiply. We're dividing by 2. And then we're subtracting the 5 on the end. So let's simplify everything. We need to simplify all of these terms individually. So our first term, notice the 2 and the 4 could cancel diagonally. If they cancel diagonally, we're left with a 25 over 2. So we're kind of doing a lot in one step. If you need to step back and do a couple individual pieces, that's fine. We're going to kind of bunch it together here. So you do whatever additional stuff you need to do to make sure you understand. So the 2 and the 4 cancel. We have a 25 over 2. We have a 50 over 2. We want to subtract that 5. Well, in order to combine that 5 with those other two fractions, we need a common denominator. The first and the second fractions are going to have a denominator of 2, so we want to write 5 as something with a denominator of 2. Well, 5 with a denominator of 2 is going to be 10 over 2. So let's summarize all this in one line. So we now have 25 over 2. Remember the 2 and the 4 canceled, leaving you a denominator of 2. We have the 50 over 2, and 5 is rewritten as 10 over 2. So now that all three terms have the same denominator, we just combine the numerators together. So 25 minus 50 is negative 25. Negative 25 minus 10 is going to be negative 35. So negative 35 over 2 is going to be our vertex y-coordinate. So 5 over 2 and negative 35 over 2. Now you're going to leave it like that. You're going to leave these as improper fractions. In order to graph, you may want to plug these into your calculator and see approximately what these numbers are. Get an actual decimal. Once you have the decimal, you can figure out where this is going to graph. You're going to have to do that to figure out where they graph. But in terms of giving an exact answer that represents the vertex, you're going to leave it in this form. This is a simplest form using the improper fractions. So we've got our vertex. It took a little bit to get there, but we found it. Now we want to find our axis of symmetry. The good news is we did all the work. The axis of symmetry is going to be easy to find once we know the vertex. So it's the x equals the x-coordinate of the vertex, which is going to be x equals 5 over 2. So that's our axis of symmetry. We didn't have to do any work to get it. Now we want our x-intercepts. So again, we're in the situation with standard form. We have f of x equal to 0. It's our standard form function set equal to 0. We can either factor this if possible, or we use the quadratic formula. If you want to avoid factoring entirely, you can always use the quadratic formula. It always works. Even when you have a quadratic that you could factor, you can always still use the quadratic formula. You're going to get the same answer either way. So if you don't want to waste any time trying to figure out if you can factor, only to find out that you can't, just use the quadratic formula from the start. So here's our quadratic formula. Our a is 2, our b is -10, and our c is -5. So plug in those particular values to the formula. And again, take your time simplifying this. We're going to simplify it all together just for sake of time, but make sure that if you need that you pause the video and simplify everything step by step. So simplify everything under that square root specifically, step by step. Be very careful with your signs. Be very careful with order of operations. So if you simplify that all down, it comes out to be 10 plus or minus the square root of 140 divided by 4. Okay, so now we need to deal with that square root. That square root is not as simplified as it can be. If we have a perfect square that divides into 140, then even though we can't take the square root of 140 evenly, we can take the square root of pieces of 140. So one perfect square that divides into 140 is 4. So we can rewrite that 140 as 4 times 35. The reason we want to do this is because we can simplify the square root of 4 even though we can't simplify the square root of 35. So essentially we're breaking 140 up into pieces. One piece we can simplify, one piece we can't. So we simplify what we can and we leave alone what we can't. So the square root of 4 is going to be 2. We simplify that part and then we just leave the square root of 35 alone. We can't do anything with that. So the only things that divide into 35 are 1, 5, 7, and 35. None of those are perfect squares, which means there's nothing else we can do with the 35. It's as simple as it comes. Now we have one more thing we can do at this point. There is a common factor among all the terms. So the 10, the 2, and the 4 have a common factor. In this case, 2 divides into all 3 of those numbers. So as long as we have something that divides into all 3 of those parts, we want to divide it out and simplify everything. So if we divided 2 into each of those terms, we're left with 5 plus or minus the square root of 35 divided by 2. So as before, that's actually 2 numbers. The plus or minus part gives us 2 numbers. So the 2 numbers are 5 plus the square root of 35 divided by 2, and then 5 minus the square root of 35 divided by 2. Those are each 2 separate x-intercepts. So in terms of an exact answer, those are the exact x-intercepts. Anything else we would do to simplify those generates an approximation. These are our exact answers. So if you want the exact answers, you leave it right there. You don't do anything else with it. Now we know we want to use this to graph. So although we want to leave those exact, in order to generate a graph, we need to be able to approximate those. So that's where your calculator comes into play. So you're going to plug 5 plus square root of 35 divided by 2 into your calculator. You'll get a decimal approximation. That's going to tell you where that's going to graph. You'll do the same thing for 5 minus the square root of 35 over 2. That's going to be another x value that represents an x-intercept. So if you do that, if you approximate those, you should get roughly negative 0.5, which is the 5 minus, and then 5.5, which is the 5 plus. So roughly speaking, just on average, our x-intercepts are going to be negative 0.5, comma 0, and 5.5, comma 0. So again, just to summarize, the exact answers are going to keep the square root. For graphing purposes, you can approximate, so at least you know where those x-intercepts fall. Okay, so y-intercept is much faster. Plug in a 0 for x, let x be 0, y has to be negative 5 in order for x to be 0. So that means our y-intercept is going to be 0, negative 5. What about max or min? So in this case, a is greater than 0. We're oriented upward, which means we have a minimum. We have a lowest point. It's always the y-coordinate of the vertex. So in this case, the y-coordinate of the vertex was -35/2. That's going to be our minimum value. We're going to use that as part of the range. So our domain, all real numbers, always all real numbers. And then our range, because we're oriented upward and we have a minimum, it's the minimum value, comma, infinity. So everything from -35/2 and up to infinity. So just like before, let's summarize everything we have. So we found our vertex. If we plug those fractions into the calculator to get decimal versions, that's roughly 2.5 and -17.5. Actually, it's exactly 2.5 and -17.5. So that's what's going to graph on your coordinate plane. Now that -17.5 is probably going to fall off the coordinate plane you're given, so just do your best. Just approximate where that's going to be. The x-intercepts you should be able to graph pretty easily and pretty accurately. So both of those x-intercepts go on your graph, and your y-intercept goes on your graph as well. So if we graph that, notice this graph is shifted a little bit to show where the vertex is going to be, where the intercepts are going to be. You should have something that looks roughly like this. So oriented upward, we've got a minimum value. We've got two x-intercepts. They're both going to be fractional. They're both going to be irrational in this case. So what we're graphing is accurate, but in terms of our values we're using to graph, those are going to be actual approximations of our x-intercepts. So to summarize what we have so far, we have two different ways of writing a quadratic function. The first one is vertex form, which, as you can probably tell, is preferable. Vertex form is easier to graph because we can graph it essentially using graph transformations. So if we consider the vertex as the point being transformed, h comma k, whatever those two numbers are in our formula, give us what we need for our vertex. So essentially we're taking the point that was at the origin for our parent function and we're shifting it around, and that generates our new vertex. Everything else after that, including finding the x-intercepts, is fairly straightforward. Standard form is what we usually have, unfortunately. Bad news, that's what we usually have. Finding the x-intercepts is quite a bit more intensive in a situation like that. We also cannot immediately read the vertex off that formula. We have to generate the vertex from the particular formula of -b/2a. That's going to give us the x-coordinate of the vertex. We plug that into the function and get the y-coordinate. Once we have the vertex and the x-intercepts, we've really done the meat of the problem, and everything else from that is fairly straightforward and fairly quick. So let's wrap up our discussion of quadratic functions with an application. So the application we're going to talk about is projectile motion. In other words, if we're throwing something, imagine standing off a cliff and throwing an object, or standing on the grass and throwing a baseball, something like that. So where does this come into play? So any object thrown from the surface of Earth follows a trajectory, otherwise known as a path, shaped like a parabola. So if we were to take into account or to strip away any outside factors like air resistance or any type of stress inside of the object we're throwing, the object we throw would follow a path that's exactly shaped like a parabola. So the reason this happens, of course, is because of gravity. If we didn't have any gravity, then whenever we threw something, well, for the first part, we wouldn't actually be standing on the earth throwing. We'd all be floating. But whenever we threw something, it wouldn't actually fall back to earth. It would just go out into space and continue on whatever path we threw it on. We all know that doesn't happen. We know it returns to earth. So because of gravity, because of the specific effects of gravity here on Earth, whenever we throw something from the surface of the planet, it follows a path that's roughly shaped like a parabola. So that means anytime we want to model something being projected, something being thrown, or something being launched from the surface of the Earth, we can model it using a quadratic function. So the function modeling the object's position is usually of the form h of t is equal to a times t squared plus b times t plus c. So you'll notice this is quadratic, but with a new variable. So the variable t represents time. In other words, the time after the object was thrown. So we're thinking of h as representing height. Height is a function of time. So time is our input, and then the output we get is going to be whatever height we're at based on how long the object has been moving. So h of t represents the height of the object at a particular time after the period when it was actually thrown. So let's look at an example. So it says a stone is thrown from a 100-meter cliff at an initial speed of 20 meters per second, so we're in metric, at an angle of 30 degrees from the horizontal. The position, in other words, the height of the stone, can be modeled by the function blah, 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 where h of t is the height in meters and t is the time in seconds after the stone is released. So we've got a lot of information here. The easiest way to deal with it is to draw a picture. It doesn't have to be pretty, it just has to be labeled accurately. So first thing we want to do is so here's our basic setup. You can think of this as the x and y axes, but for our purposes, think of it as the cliff and the ground. So the vertical axis represents the cliff we're standing on, and then the horizontal axis represents the ground that we're throwing the object from. So y is equal to h of t. In this case, our y coordinate represents h of t, which is the height in relation to a period of time. And then what we think of as the x-axis, we're actually going to think of in terms of t in this case. So t is the variable that we're thinking of as the input. So we're standing at 100 meters high and we throw an object off the cliff. So notice if we draw the entire parabola, part of the parabola is going to be going into the cliff itself. We're going to have to deal with that in a minute. But in terms of the actual application, the actual situation that's occurring, we're throwing it off the cliff because whenever we throw something, it follows the path of a parabola. It's going to peak at some point and then it's going to fall and it's going to hit the ground at some point. So some t, think of it as a time t. So this is the point where it's going to hit the ground. And then height at any given time is modeled by the function we were given. So negative 4.9 t squared plus 10t plus 100. So we were given information about the initial speed. If this were a physics class or a differential equations class, we would have to use that. But because we were given the actual function we need to use, we don't actually need that information. That's extraneous information that doesn't actually tell us anything additional that we need to know. So all we need to know is what this function looks like and how this function works. So first thing we want to do is we want to know at what time will the stone be at its maximum height. So keywords are time and maximum. Whenever I see maximum in the context of a quadratic functions problem, maximum always corresponds to a vertex. So anytime I see the word maximum or minimum, I'm talking about the vertex. And I want to know at what time is the vertex going to reach its maximum height. Well, remember, time is our x-coordinate, height is our y-coordinate. So if we put those two pieces together, that means we're looking at whatever the x-coordinate is for the vertex. So maximum means vertex, time means we're looking for the x-coordinate. Well, because our function's in standard form, we can't immediately find the vertex from it. However, we have a formula that allows us to determine it. So the x-coordinate is going to be negative b over 2a. So we just plug in our particular values for a and b. In this case, b is 10 and a is negative 4.9. If I simplify this down, negative 10 over negative 9.8, it's going to be 1.02 seconds. So again, because we're talking about time, the unit is going to be seconds. So after 1.02 seconds, after throwing the stone, that's when it's going to reach the maximum height. That's when it's going to reach the vertex of that parabola. So there's one piece of information. What is the stone's maximum height? And we want to round to the nearest meter. So again, keyword maximum. We've got that word again. So maximum means vertex. And since we want a height, now we're looking for the y-coordinate of the vertex. Well, I know what the x-coordinate is, or in this case, the t-coordinate, if we're thinking of t as the input. If I want to find the output that goes with that, I just plug in the input value that I just found. So I'm looking for h of 1.02. I plug that into my function. Order of operations, as always, make sure you attend to precision there. Roughly 105 meters. So that's going to be my maximum height. That's going to be the y-coordinate of our vertex. That's the highest point that our stone reaches before descending. And last but not least, at what time is the stone going to hit the ground? Well, if you think back to the picture we drew, the stone hitting the ground represents the x-intercept. Where is it going to hit the ground? We're looking for the x-intercept. So hit the ground means x-intercept. Now keep in mind, if it's a parabola, we technically have two x-intercepts. Well, it only hits the ground at one time, so let's just find the x-intercepts and see if we can interpret what information we need based upon the situation we're in. So this one definitely doesn't factor. We definitely need the quadratic formula. So as before, if you need, pause the video for a second, simplify everything, specifically what's under the square root. Make sure you can simplify that. Now keep in mind, we're just going to approximate here. If we're in a real world situation, we're not looking for an exact answer, we're looking for a reasonable approximation. So if we simplify this down, negative 10 plus or minus the square root of 2060 divided by negative 9.8. Again, these are two numbers, so plus gives us one number, minus gives us another number. If you plug those two into your calculator, you will get two separate values. We're going to approximate them, so let's approximate them to two decimal places. So if you approximate there, we get negative 3.61 and 5.65. So is this telling us that our stone hits the ground at two different times? That's what it seems like it's saying. But since we're talking about time, think about the actual situation. We're talking about a time in this grand scheme of things, the time after we've thrown an object. Because we're talking about time, negative 3.61 doesn't actually make any sense. That's a negative time. Well, if you think about what our picture looked like, remember we had an x-intercept that was conceptually going back into the cliff. Well, obviously that's not going to happen. Obviously we want the x-intercept that's out past the cliff on the ground. So the answer we want is going to be the 5.65 seconds. So even though there are two x-intercepts for our parabola, only one actually fits into our particular problem. So let's summarize this admittedly very long section by reviewing the two different forms we have for quadratic functions. So our first form is vertex form. Vertex form essentially looks like the form we would use to graph if we were using transformations. So we have a number out front that's going to tell us the orientation of our graph, and then h comma k is going to give us the vertex for our graph. So it's going to give our highest point, our lowest point, depending on how our graph is oriented. Our axis of symmetry is always going to be x equals h, whatever h is. So h is the x coordinate of the vertex. And again, make sure you attend to precision here. So the vertex is a point, the axis of symmetry is a line. So if you're finding the axis of symmetry, you're finding an equation of the line, keyword equation. So that x equals part is very important. If you just write h is just a number. X equals h is an equation of a line. So that's vertex form. Once you have these two components, it's pretty easy to find everything else. Make sure you find your intercepts, and then that typically gives you enough information to generate a pretty accurate graph. Our other form for a quadratic function is standard form. So if we were to take vertex form, multiply x minus h by itself, in other words, square it, distribute the a out front, add the k on the end, we would end up with something that's in standard form, which is ax squared plus bx plus c. Standard form is more commonly used. It's more useful in some situations, but in terms of graphing, it's usually slightly more difficult to graph from standard form. So because we don't immediately have h and k in terms of positioning in this particular functional form, we have formulas in order to find them. So in order to find our vertex, the x-coordinate is going to be negative b over 2a, using whatever a and b are in our standard form. Whenever we want to find the y-coordinate of the vertex, we take the x-coordinate and plug it back into our function. That gives us the matching output for that specific input. Once we have our vertex, the axis of symmetry is just going to be x equals whatever the x-coordinate is for the vertex. So you don't have to use the formula again. Once you've used the formula, negative b over 2a, one time, you're just going to carry that number, whatever that number is, through the rest of the problem. And then typically, when we're in standard form, once we need to solve for our x-intercepts, we're going to have to use the quadratic formula. Now, there are plenty of situations where you could factor, but unless you're very, very comfortable with factoring, I would recommend just using the quadratic formula by default. It's possible that you could try to factor, only to find that you're going to have to use the quadratic formula anyway, and then you end up having wasted a little bit of time.